Picture this. You walk into an office, set a tiny coin-sized chip on the desk, plug a fiber line into it, and boom! You've got quantum power running at room temperature. No steel drums, no liquid helium, no space-age freezers humming in the corner. Sounds wild, right? Well, that's exactly what a Stanford team just inched us toward, with a breakthrough that uses what they call twisted light. Here's the thing. Most quantum computers today have to sit colder than outer space. That's how fragile their quantum states are. Stanford's chip laughs at that cold-only rule. It sits on a warm bench and gets the job done anyway. Let's unpack how they pulled that off, why the twist in the light matters, and what it could mean for everything from secure networks to AI crunching. First, the big mindset shift. Instead of fighting heat, Stanford is choreographing around it. Think of background thermal noise as static on a radio. If you design your song, the quantum signal, to live in a frequency that static can't touch, the tune plays on, no matter how loud the room gets. That's the philosophy here. So how? They match three things at once. 1. The twist, or orbital angular momentum of photons. 2. Specific electronic states in a 3-5 semiconductor stack. And 3. The standard telecom hardware that already fills our data centers. Get all three dancing in sync, and suddenly you've got a quantum system that shrugs off room temperature. Now let's zoom in. Picture a tiny traffic circle for light. The integrated waveguide on the chip naturally wants to support spiral patterns, light that corkscrews as it moves. Pump energy in, and the semiconductor's electronic transitions act like little antennas, popping off photons that already fit that corkscrew shape. Because conservation laws have to be happy, those photons come out in matched, twist-correlated pairs. In other words, the waveguide isn't just tubing. It's a built-in, nonlinear crystal with its own self-filtering rules. Stanford reports 90 plus or minus 2% fidelity over billions of emission events. That's the consistency you need if you ever want to scale beyond one flashy lab demo. Okay, 1550 nanometers. That's the color of light that zips through the fiber already under your city streets and across the ocean floor. Because the chip speaks that language, you can plug it straight into today's amplifiers, filters, and switches. No special cables. No cryogenic island. Just clip it in line. Here's a quick use case. Drop in quantum key distribution across a metro fiber loop. Swap only a handful of nodes, and you've got nearly unhackable links. In a data center, the same chips could live beside classical GPUs, translating between solid-state qubits and photonic twist modes that carry correlations across racks. You might ask, why not just add more emitters and call it a day? Because the real trick is orchestrating interference among many twist channels without letting them talk over each other. That pushes designers toward richer on-chip photonic circuits, rings, interferometers, reconfigurable phase shifters, the toolbox silicon photonics already uses for wavelength routing. Think of each room temperature chip as one site in a synthetic crystal. Wire many sites together through fiber, and you can engineer whole bands of orbital angular momentum channels, where information flows along preferred pathways, very much like electrons do in real crystals. Another analogy, photonic topological insulators. There, special waveguides force light to hug the edge of a pattern, immune to bumps and scratches. Here, we could design pathways where only specific twist patterns survive, using the rest as guardrails against noise or eavesdroppers. Let's make this concrete. Secure links. Quantum boxes can sit in ordinary racks next to Wi-Fi gear. Rolling out a secure lane on an existing fiber route becomes a line card upgrade, not a building renovation. AI and optimization. Imagine accelerator cards that handle only the gnarliest correlation steps. Hours of compute shrink to coffee break time. Sensing. Lunchbox-sized field units ride in planes or trucks, using quantum effects without a rolling cryo lab. The key point? Quantum gear starts looking like just another component in the engineer's toolbox, not a cathedral-scale science project. Remember how Wi-Fi went from novelty to invisible assumption? Room temperature quantum nudges us toward that same normalization. Let that sink in for a second. So, where could this sneak into your day-to-day? Maybe in supply chain optimization, fraud detection, or simulation. Whatever your field, start scoping the problem that keeps you up at night, the one you'd hand off to a quantum coprocessor the minute you could. And while you're at it, pick one bite-sized skill: photonics basics, twist modes of light, or error correction schemes. Spend even an hour this week reading or watching a tutorial, and you're ahead of the curve for when these warm chips land. So here's what we covered today. 1. Stanford's new chip uses twisted photons and a carefully tuned semiconductor to run quantum operations at room temperature. 2. By matching 1550 nanometer telecom wavelengths, the chip can plug straight into the fiber infrastructure that already circles the globe. 3. Scaling isn't just about quantity, it's about choreographing many twist channels with on-chip photonic circuits, creating synthetic band structures that move information cleanly. 4. Room temperature quantum opens doors. Secure city networks, faster AI accelerators, and rugged field sensors, all without cryogenic overhead. 5. Your action plan. Identify the hardest problem you'd offload, learn one supporting skill, and connect with a lab or startup pushing twisted light quantum tech. If you do just those 3 things, spot a use case, level up one concept, reach out to one person, you're already part of the story. Quantum is leaving the freezer. The question is, will you be ready when it walks into the room? I'm Men, and this was your 10-minute deep dive into room temperature quantum computing. Subscribe, share, and join us next week when we explore another frontier tech that's quietly rewriting the rulebook. Until then, stay curious.